Special thanks to Elon, who's recording in the back for us, and also coordinated with the speaker today, Ross, and helped get everything situated. I'm Brandon, as I said, and the president is sitting right here. Mate, don't get us confused, we look really similar, but his English is way better than mine. And Ross is our speaker today, as I mentioned. So everyone, warm welcome for Ross. And side note, I don't know if anyone knows this, but Ross just got engaged, so I'm going to dox you.
Not yet.
Not yet?
We can't show that. We can't show the recording.
Don't worry, I'll wait to post it.
Censor that. Censor that.
Okay, great. Well, congratulations on your soon engagement. Whoops. Okay. What's up? Yeah. And then, okay, great. And so, yeah, we have at least one of the winners of our contest in October from Ratatouille on Embedded Systems. We got, for those of the, I'm going to say all of them because I don't know who's here. Jose with his BPM counter. Jose's here. Come get it. Come get your ESP32T display. Really good. Nice. Yeah. It's pretty awesome. If you haven't seen, we did post the video of that whole thing, and at the end of that video is Jose's demo and a bunch of others. So also Armandas, please forgive me.
Nobody else is here.
And Colin, who are not here. So congratulations. Yeah. Thank you. Thank you for your help. All right. If you're seeing this video and you're these other two people, come to the next meetup so we can give you your prize. We're going to keep doing this until everyone has them, so please.
There's only one left.
Yeah, all right. So that's basically it. The last slide, just a little call to action. If you love Rust and you love Tokyo, then you love Tokyo Rust. So please come give a talk, come volunteer, give us money, or if you have any ideas at all, please just come talk to Mate or myself, or send us an email at contact@tokyorust.org. And one last thing that's not on here, if you haven't seen it yet, we updated our our website to accept contributions of community projects. There's already 7 or so on there. Some of mine, some of Mate's, some of Luke's. There's some really cool stuff. There's a talk on Mork from the last, from this event we had last week with Linux. Some of you were there. Oh yeah, and so Mork's on here. It's really interesting. So please do that. You just need to make a quick pull request, and there's a little script that does it for you that I totally wrote and didn't delegate to an agent. Yeah, and that's it. So please welcome Ross. I'm really happy to excited to unpack cargo. So thank you, Ross.
Thank you. Let's see if it's... All right, we're good. All right, yeah. Hello, everyone. I'm Ross. Let me go ahead and just jump right into it. So, that's me. Yeah, I'm Ross. I'm from the United States. I've been here in Tokyo for 3.5 years or so. I'm a Rust and open source enjoyer, and I'm at Ranger Ross on GitHub. So yeah, that's just me in a nutshell very quickly. And today I kind of wanted to talk about some of the work that I've been doing in cargo over the past year. And so I'll go into kind of the motivation as to how we ended up here. And then we're going to talk about how cargo works, because if you don't understand how it works, I don't think it's very interesting. So I think that's actually the most interesting part of the talk. Then we're going to talk about the improvements that we've made over the last year, and then what we have planned. And so that's kind of the outline of what we're going to talk about today. But first we have to go back, really far back to 2024. And I was working on Rust, and I was kind of the first person at my company to use Rust. And I was working on a feature. And of course, if you're at a company and you're working on a project and you open a pull request, in the perfect world, you have CI that runs, right, and make sure that your build runs and your test pass. And we did, right? I set it up, and I have Jenkins running, and it's building, and it's still building to this day. But yeah, if you're new to Rust, the compile times are maybe not the greatest, and I was really sad about that. That was, yeah, literally me, right? And so if you're a DevOps person in the room, you're screaming just to add a cache, right? And so like, that's the easy way to like fix slow CIs out of cache. And fantastic news for us, there actually is a really good one called SC cache. And this is a cache that's really popular in the Rust community, but also works for C and C++. And it basically caches compilation output. And it's really nice because it has like first-class integrations for like AWS 3 or any kind of like storage provider that you want to use, right? So I added that, and the build went down by like 10 minutes. That's great, right? Thank you for watching. But hold on, let's go back. What's going on for this 5 minutes, right? We cached it, right? like we're just waiting here for 5 minutes doing nothing. And well, if you go read the fine print of SC cache, there's actually some caveats. And the one that we're kind of interested in is that, I'm not sure if you can read it, SC cache doesn't cache a lot of create types. So for example, binaries or proc macros, so SC cache doesn't even try to cache those. So if you've ever had someone that, like you've ever talked to anyone that says like, hey, I've tried SC cache, but like I didn't really get a lot of benefit from it. Like it didn't really work on my project. And I think a lot of the time, it's because of these caveats. Like their project is just using things that can't be cached. For my scenario, when I was doing this, I saw a fantastic benefit. So like it was like a no-brainer to keep it, but your mileage may vary, right? Yeah, so it's pretty conservative on the crate cache, like the crate types that it will cache. And it also doesn't have a lot of context about the build dependent, like your build tree, and like all the information that Cargo has. Because if you don't know, SC cache just intercepts the command line like arguments that are passed to Rust C, and then it does its best to figure out what it can cache based on that, which means that it has to be pretty conservative, or otherwise you'll get stale cache reads. And of course, you have to install it. So around this time, I was like looking at like, is there a better way to do this? Like, do we have anything that like, anything on the horizon that would make this better? And we did. So this is a Rust project goal from 2024 H2. And this was to add a user-wide build cache to Cargo itself. And it was proposed by Ed Page. And I was really excited about this. I was like, yes, we're going to get it like as a first-class citizen to Cargo. And since Cargo knows like way more about the like dependency tree, it can be way more aggressive, right? And like here's the tracking issue for it. But you're going to notice like something's missing here, right? There's no owner, right? No one was driving this. It was proposed by the Cargo team as like, hey, we'd love to have someone come build this, but we're not going to, right? Or at least it's not the highest priority, right? And so like 2024 went and passed, and then I kind of was like, okay, I'm going to ask like, hey, maybe I can help do this. And so this is a message from me in the Rust zulip. The message here is not super important, but it's just me posting saying, hey, I want to try to help like push this forward, even though I don't really know anything. So that's like how it kind of started for me. So now we're going to switch gears, and we're going to talk a little bit more about like how Cargo works, and then we'll continue our little story, okay? Yeah, so that's motivations check mark. So if you are not familiar with Cargo, Cargo is not a compiler. Cargo is just a build orchestrator, and it calls out to Rust C, right? And so if you run Cargo build-v, it will actually like print out like what it's actually executing, right? So it's kind of hard to see, but there's a Rust C here that it calls out to and compiles, right? And it's a lot of arguments, right? And so basically Cargo just runs Rust C in a loop a bunch of times to compile all your crates, right? But we need a place to put all of these files in between, like in between Rust C compilations, right? And so you probably know this as the target directory, right? This is where your compilation output goes, right? So it has like your binaries whenever you're finished compiling, but it also has a bunch of like crazy files that you probably never had to like look at or think about. And today we're going to think about them a little bit and look at them right now. So I'm going to kind of like quickly just go through like the anatomy of the target directory as like how all the files are laid out. Hopefully everybody can see this. I made this like better previously. And so the first thing you'll notice at the very top is debug, right? And I think you may be familiar with this. So this is the profile, right? And so you're probably familiar with like cargo build -- release, right? That'll build into the release profile. So cargo organizes by profile first. And this will also be nested inside of like the architecture if you target like a platform that's not the host, right? So if you target like x86 unknown Linux GNU, it will like nest the profile in that folder. And importantly, we have locking at the profile level. We'll come back to that in a sec, right? So that's like the profile. And then the next thing is the binary, right? So this is like probably the most important thing for you as the user, right? You have like your binary output. So this, whenever you build your program, this is what you usually care about. So we'll move on. There's a .d file, and that is a dep info file. And we're going to talk about dep info files later. But basically, it's for external build systems for this one. The next folder is the build folder, right? And so the build folder is where all of the build script stuff goes. So maybe I shouldn't have put proc macro 2 as the example here because it's a bit confusing. But basically, if you have a build script, it's going to put all of the files, all of the output associated with running that build script. And you'll notice that they're actually like different structures. And that is because the one of these folders with the hash has like the actual build script like binary that you're going to run. And then you also have another one which is like the execution of the build script. So like we break these up into two different build units, and we'll talk about build units in a second. But that's what the build folder is for, is where all of your build script stuff goes. The next folder is the deps folder. This is the most important one for Rust C. This is where all of like your library output goes and all of like the metadata. And this is like basically where we point Rust C at. And Rust C goes and finds everything that it needs to compile, right? So this has rmeta and rlibs, right? So if you're not familiar, rmeta is like a metadata file that's produced by the Rust compiler, and then rlib is like the library file that has like all of the compiled library code. And we use those like down in later Rust C invocations, so we kind of feed those back into Rust C, and eventually you get your output, right? Examples, I think that one's pretty straightforward. It's basically where your examples get compiled to. There's not really much to that. There's also this fingerprint folder. And you may or may not have seen this because it's like got a dot in front of it, so it's hidden. So if you do like an ls or a tree, you won't see it. And this is what Cargo uses for rebuild detection. So if you change your project or you pull in, or maybe like you upgrade a dependency, it uses fingerprinting to like detect if we need to rebuild something. And we're going to talk about more about fingerprints in a bit, but just know that's like there. And then finally, there's the incremental folder, right? And so the incremental folder is actually very opaque to Cargo. This is for Rust C incremental compilation. So this is like within a crate, you can have incremental compilation. Cargo has like very little knowledge of this. I don't know what any of these files do. And we basically just let Rust C like have at this folder, and hopefully it makes your builds faster. Fun fact, we only actually like turn on Rust C incremental compilation on local crates because there's not really a need to. If you like pull in a crate from crates.io, you're not really going to change the source of that, right? So we don't turn that on because there is overhead with like turning on incremental compilation. So it's just like a fun fact. So like that's the anatomy of the target directory. I hope maybe like that spreads like some like lore about it. Yeah, so this is like, so we're going to talk about how Cargo compiles. Like, so the first thing Cargo does is it reads your Cargo toml and your environment, and it parses out and like builds a configuration object that Cargo is going to use down the line. And then it solves your dependency tree, right? This is like Cargo's most important thing is, being a package manager, right? So it solves all your dependencies and it downloads any that we need that aren't already on disk. And then it converts the dependency tree into a build graph. And the reason we do this is because crates can actually have more than one build unit. So if you have a crate that has a build script, for example, a build script I just showed had 2 build units, plus you have like the actual library, right? So that's like 3 build units for one crate. So, and we actually need to like make sure that the graph orders these all correctly so that they all compile and like are executed in the right order. So we convert it to a graph. Then we take that graph and we look at all the fingerprints and we check if there are any like dirty jobs, right? If there's any code that has changed on any of our build units that we need to recompile, maybe like a Rust flags has changed that we need to recompile. And we schedule out a bunch of compiler jobs, right, that call out to Rust C. And then we just execute those all in parallel. And Cargo has like some like scheduling rules, like make sure that these get like executed in the right order. And then finally, when everything's like all of these compile jobs are done, we update the fingerprint. So next time we compile, we don't need to rebuild it. So that's like how Cargo compiles. Demystified. Okay, so I mentioned fingerprints and dep info files. And I wanted to go into that. So fingerprinting, it determines if a build unit is dirty or fresh. And when I say dirty, it means it needs to be rebuilt. Fresh means that it needs to be like it's good the way it is, which kind of is a bit odd because I thought at first fresh meant like, oh, it's fresh, it needs to be cooked, right? It needs to be rebuilt, but no. Oh yeah, so the fingerprinting actually tracks like a bunch of environmental changes. So if you have like environmental variables or file system like dependencies, fingerprinting can track that. It can also track like build script directives, right? So if you've ever had a build script that uses like cargo rerun if, and usually you pass like you put like an environmental variable there, Cargo would like track that and make sure that if you change that, it would rebuild. And there's actually 4 of these. I gave a previous like practice run of this, and I had 2 here. And I talked to one of the Cargo team members, and he's like, actually, we have 4. But for the purposes of this discussion, there's only 2 that are important to us. There's the rustc.d files, and then there's like this cargo specific dep info file. And then we have like some unstable like binary dep info files. So remember at the very beginning, I showed a picture of like my binary.d. So that's a rustc dep info file. And whenever rustc compiles your crate, it uses that to, it basically keeps track of everything that your source code has like reached out and like, into your environment and grabbed. And it keeps a track of everything so that way we can like know what your crate is like reaching out to you. And then, yeah, we have a cargo specific one. So we basically translate the dep info file from rustc to the cargo one. And I'll talk about why we do that in a bit. I want to give some examples to like, okay, so here's everything that fingerprinting tracks. So it's kind of hard to see, but basically all of these things in this list here, fingerprinting will track for you. Not super important, but I just wanted to show that it's a lot. So I wanted to give an example as to like what I mean by like rustc reaching out into the environment. So if you've ever used like the .env macro, you know that like it reads this environmental variable at compile time, right? So if you change this environmental variable, you need to recompile, right? And so if I actually like cat out the rustc dep info file that's like created from this, you'll see at the very bottom here, we have like rustc is tracking, like it said, hey, this source code, it reached out and it needed this environmental variable from the environment. And then Cargo is going to use that to track if things need to be recompiled. Yeah. So why do we have 2 formats? I guess I should have updated this slide to say 4. And the reason is because if you look at the last slide, you'll saw that there were like absolute paths in the file as well. So if you move your workspace, you'd have to recompile everything. So Cargo tries its best to like avoid rebuilding if it doesn't need to, right? It would be really annoying if it like constantly rebuilt when you didn't need to. And so yeah, so Cargo normalizes that as well as it enriches like the dep info files with other information. So we talked about like the build script directives. Rust-C doesn't really know about the build script directive. That's a cargo feature, not a Rust-C feature. So like the cargo dep info files will have more information, like from like build scripts and stuff that Rust-C might not have. And then also, the cargo dep info files are really optimized for fast write or fast reads. So we use this funky format that I don't really know. I don't really know how it like determines like where this starts and stops, but it's really optimized to like go fast. So that's how cargo works. So why do we want to like why change it, right? Like, and well, one of the problems that we have is that we're looking at our target directory. If you want to compile a single build unit or a single crate, you end up touching like a lot of different directories, right? And this is kind of a bit painful because like we need to lock the entire directory, and we can't really do like efficient caching because like, are we going to cache like this specific folder and then this specific folder, and we need to keep track of all the hashes. So like you can't really have like fine-grained caching. You know, there's tools out there that kind of help you do this, but it's not super great. Yeah. One of the other funny things that we've probably all experienced is if you've ever done like a cargo add and some dependency, and then you've immediately done a cargo build, and then you get blocked down here because the directory is locked, because we have to lock the entire thing during a build. Yeah, this is literally everyone, right? Right, yeah. Like that waiting for lock is really annoying. So why does that happen? And so you modify your dependency tree in some way, right? And then in the background, you usually have like some LSP, right? Usually it's Rust Analyzer. That's the most like popular, widely used one. And internally, that uses cargo check. So I think in VS Code or whatever, it will say like running cargo check or whatever. And this will lock the target directory. And so whenever you try to execute your cargo build, it's locked because your LSP is running. So that's like kind of a problem. Another pain point is like if you've ever had a long running like project that you've done a lot of builds on, that target directory gets pretty big, right? It grows, and like I've had directories where I've had like 20 gigabytes in my target directory. Who has more than 20 gigs? More than 50 gigs? 100 gigs? How many?
240.
Oh, fantastic. Yeah, okay, so it gets pretty big, and so we want to try to reduce this space. So here's the plan. Okay, well, I don't know why I put that slide here. Yeah, so this is what we've done so far. So the plan is we're going to split the target directory into 2 directories. All right, so hear me out on this. I know it's a bit crazy. So we're going to split it into a build directory and an artifact directory. And I'll go into details on these in a second. And once we split these out, we're going to reorganize the file layout of the build directory by build unit plus hash so that we can have like units to lock on and cache on. And then finally, hopefully switch to fine-grained locking for the build directory. And then add our user-wide like cross-workspace cache. And then the final step in our plan is maybe, just maybe, we can add remote caching support with like a plugin ecosystem into Cargo. And so we're going to like walk through the steps of this plan that we have and like show what we've done. So the first step in our plan is to split target into 2 different directories. And the first directory, builder, this is where Cargo is going to store intermediate build artifacts. So this is stuff that like comes out of Rust-C. This is like fingerprinting, like internal things to Cargo. This is probably stuff you don't care about, right? This is like just a means to an end, right? You don't care about a dep info file. You care about the binary at the end of the pipeline, right? And then there's artifact directory. And this is where Cargo stores like what we call final artifacts. And this is the stuff you probably do care about, right? This is the binary from your Cargo build. This is like HTML output from like Cargo doc. or like cargo build dash dash timings. We have the HTML report. So anything that you, the user, want to consume is going to go into the artifact directory. And here I put like an example of like what would go on here. So up here in the top left, I do a cargo build, but I specify the builder as like just build instead of target. And after like it builds, we do a tree on target, and you'll see that it's actually not a lot going on here now, right? Like we've only got the binary that we really care about. And then in the builder, all of the extra stuff that is associated, like that we needed along the way, is in this thing, right? And so what about backwards compatibility? Because I know that's like what everyone in here is thinking about, right? Like there's no way on earth that we're gonna like split two directories that would like make the Rust ecosystem explode. and you're right. So what we did by default is builder and artifactor both point to the same directory. And so they both point to target in your workspace, right? So ideally you wouldn't notice it, right? So there's no change in behavior. It's still, all of the files still go to the same place currently. We just give you the ability to overwrite it. And so you can still like specify cargo target dir, but you can now specify cargo build builder. The build is because of how cargo's naming convention works. We had a discussion about cargo builder. We decided not to do it. That's its own topic. And then you can also specify cargo build artifactor if you want to override the artifactor. Artifactor is still unstable, so you can't use that yet. But one of the other things that we want to do is eventually we want to change the location of builder to be in a shared location. And right now we're considering cargo cache home, like cargo home, like the .cargo in your home directory. And then we're going to like keep it separate for each workspace. So that's an open issue that we have. And I'll go into more details on this in a second because this might be like, it's still open and there's discussion going on about that. So is anybody here nervous about backwards compatibility? Yeah, you? Okay, yeah. It's already stable. So we stabilized this a couple of months ago, and we haven't really had anybody having issues. So yeah, it was in Rust 191. This was stable. So, woohoo. So yeah, I think so far no issues that I'm aware of. Alrighty. So next we're going to talk about reorganizing the layout of the build directory. So we want to reorganize the files into like build units into a single directory. So that way when we build something, it all goes into like one single location. And that way we have like a single directory we can cache and lock on. And so like this is kind of like what we have proposed currently. Sorry, it's kind of hard to like put the text here, but basically we moved all of the files from all over the place and they all just go into the build folder now. And then we put it into the build unit with the hash. And then we kind of just kept the like similar structure as previously because it was easy. We didn't really put a lot of thought into like the internal structure. But yeah, this is what it looks like. And so this change was actually pretty easy. This is on nightly currently. And so you can access it with -z builder new layout as an unstable flag. But it really doesn't help much currently because it just reorganizes stuff. So like you don't really get any benefit from reorganizing the layout if that's all you do. Right? It makes maybe the cargo team's life a bit easier, but we haven't really stabilized it because we don't want to cause like a lot of churn in the ecosystem for something that's not really benefiting anybody. Yeah, so what we want to do is we kind of want to bundle this with another feature that's actually useful to people. Maybe that would help us like ask for forgiveness when we make a breaking change. One of the notes before I go into fine-grained locking is the builder, everything I've shown so far, these are cargo internal. So like we reserve the right to change these. Artifactor is stable for you. So like you can assume the layout of artifactor will not change. We will not break that. But Builder is like, up to our discretion. But we do recognize that like a lot of tools rely on the directory structure, so we're trying to minimize that as much as possible. Okay, so fine-grained locking. So this has been an open issue since 2017. And basically, we want to avoid the problem of running into like waiting for lock whenever Rust Analyzer runs in the background, right? And so to do that, we need to have like fine-grained locking on like at a build unit level. And to do that, the plan is just move the lock into the build unit, right? Surely that shouldn't be too bad, right? Right. So before I go into like how that worked out, so how locking works in Cargo. So we use file system locking. So that's implemented in Linux using flock2 or just flock. And then it's implemented on Windows using the lock file ex. I don't like the way Windows names their stuff. Anyways, so this is advisory locking, which if you're not familiar with that, it just means the operating system will keep track of the lock and if it's locked, but it doesn't actually prevent you from reading. It's on the program to like actually obey the lock. So some other program could come in and like read and write, and there's nothing preventing that. But usually it's not a problem. And plus these are very portable. One of the things we have to think about with Cargo is it needs to run on like every computer under the sun. And so trying to like use anything more advanced is really difficult. So yeah, this is what we got. And it works pretty well. We haven't really had any issues with it, even though it like sounds really scary that it's just advisory. Yeah, so advisory locking, you can take locks as a shared lock or exclusive. And that'll come into our design later. And then right now it's at a profile level, right? We talked about that. It had the .cargo lock at the profile. So whenever we try to move the lock into the build unit, I opened a pull request on this, and like it's kind of foreshadowing that like the red closed is like it was a bit more complicated than that. And one of the issues is that we have like this feature in Cargo called pipelined builds. And so what Cargo will do as an optimization to speed up builds is it will compile your crates and all your dependencies. And as soon as the metadata from Rusty is done, it will start the next compilation. And so we talked about our libs and our meta. So it'll wait for our meta to get complete. But even though our lib, the actual library, is not compiled yet, we'll start compiling the downstream. And the reason we need to do that, like the reason we can do that, is we actually don't really need the R lib until we link. And so like the way you would kind of visualize that is you can compile your library crate, and as soon as the R lib is done, the R meta is done, you can start compiling like your binary, your downstream. And as long as you finish compiling your R lib before linking, you're good. So this is like an easy optimization that we have had since like Cargo 138. And from my experience in my testing, this is like a 10% improvement, right? And yeah, so whenever we open that pull request, you'll see it's kind of, you may not be familiar with the timing chart, but basically it's these orange little markers are like when our meta is produced. And you can see as soon as we finish our meta, we start our build for the next one, and we just lock until the end of the compilation. So just doing like a naive locking approach completely like negates the improvements of pipeline builds. And so like I think people would not be like too welcoming of this change if it resulted in a like 10% performance reduction across like every build for like the off chance that you get the like have better locking and better concurrency builds. So this is something like we're not willing to compromise on. All right, so we need to support pipeline compilation, and to do that, we need a stateful lock, right? We need a more complicated lock. Yeah, so what do we need from our lock to like make it work, right? And one, we need to be able to take it exclusively while compiling, so other cargos don't like try to read while we're changing things, right? We need to be able to like downgrade it, so readers can read the R meta once it's produced, but we need to like make sure that like, we're still compiling, right? So we need to make sure that, yeah. So we can't have multiple writers, of course. We need to be able to take it as shared, right? So if you have like two things reading a dependency that's already been compiled, like you should be able to, in theory, have unlimited numbers of cargo read that dependency. Yeah. Because, yeah. I don't really remember what that was for. Yeah, and we need to be able to take it as shared with the guarantee of no writers, right? So whenever we link, we need to make sure that there's no writers, because if there's a writer, there's a chance that the R libs have not been written yet. So we need to like be able to handle that as well. So this is like the flock 2 implement like man page for Linux. And if you look down at the bottom, oh, I thought I had an arrow. If you look down here, we have like the possibility of a shared lock or an exclusive lock, and that's really all we can get out of like a file system lock on Linux. So the idea that we had, and one of the things that we've been exploring over the last few months, is using multiple files to represent the lock and having like a stateful lock. So you can kind of imagine 2 locks. I have like one called partial lock and one called full. The names don't really matter that much. And so like you have these locks, and if they're both unlocked, it's unlocked, right? And whenever it's time to go and like compile, we take both of them exclusively, right? And so we are in this like building exclusive state. And we're like compiling the R meta, right? We know that we're the only one in this section that can read, or that can write or read, because we have exclusive locks to both. But whenever we finish the R meta and it's time to like continue actually building the library, we downgrade the partial lock to a shared lock, and we allow readers to take that lock as a shared lock and read the R meta. And that way we can like unblock pipeline compilations. And then like from the inverse side, like if you're a reader and you're building like a downstream dependency, you're going to take a shared lock, and we're in like this shared partial state where we can read like R meta, but we're not allowed to link in this state, right? And then once it's time to like you're at your like final binary and it's time to link everything, you take a full shared lock on all your dependencies up the tree, right? And this will guarantee that there's nothing like still left compiling, and there's no like other cargoes out there compiling either, right? Oh, hello GNOME. Thank you. So that's kind of the idea, like one of the ideas we have. And so like here's like kind of the same thing in like the cargo doc format that we've like written documentation for. Food for thought. State's probably a bad word because you can have multiple states at the same time because it's like a concurrent system. So I don't really know what to call it. I'm calling it state, but someone else probably knows a vocabulary word that's better for that. Okay, so there's some caveats to this, right? Like there's trade-offs with every design. One of the really important things is we have to always take the locks in the same order. Like we can't just take them in reverse, otherwise we would deadlock, right? This increases the amount of file descriptors in cargo by a lot, which is really unfortunate. And a lot of operating systems will have like file descriptor limits per process that we need to like be aware of and handle. Usually it's like on most like modern Linux distros and systems, it's not that big of a deal, and because you can just raise it. And then we just need to be aware of like general performance implications, which I haven't really had any issues with that so far. Spoiler alert, we did not go with this design. We decided this week that we're going to change the design a little bit. Probably for better, because like having 2 locks per build unit is probably a bad idea. Like it's really overcomplicated. So we're still ironing out the details on design of locking. Yeah, it's still a work in progress. You'll notice that there's over 90 comments on this pull request. and a previous pull request attempt. So we're making progress, but it's a little slow, and we're trying to be like cautious about breaking anything. Here are all the open issues that we have for locking on this pull request. That's why one of the reasons it's not merged. So what about artifact directory, right? Like we've been talking about build directory. And actually, we decided it's okay. We can just keep coarse grain locking because we just need to lock it and like copy up the files that we need to like give to the user. And one of the assumptions that we're making is that 2 cargo builds at the same time are somewhat rare, but cargo check and cargo build are very common, right? And so we're kind of optimizing towards like real world use cases instead of hypotheticals. In a perfect world, and it'd be nice to be able to do 2 cargo builds at once, but you know, I think this is a fairly easy like change that we've made, and this is the trade-off we're going to make probably. So this is actually on beta. Fun fact: there was a bug discovered in this on beta, and I had to backport it this weekend. I had to backport a bug fix, which scared me a little bit because like it made it to beta, so we almost made it to stable Rust, which is a bit scary, but thankfully someone reported it. So that's what we've done so far over the last year. It sounds like not that much, but in like in terms of all volunteer effort and the like complexities of like making sure that everything's backwards compatible, I think we made a pretty good progress. Okay, so I want to talk about like the vision I have for caching and like what we've discussed on the cargo team. So we're going to talk about the user-wild cross workspace build cache. So isn't builder like the cache, right? That sounds what it is, but actually like we're probably not going to do that. And there are some reasons we want to avoid that. And so it kind of suffers from the same problem of cargo targeter. Like if you share that across workspaces, which I know a lot of people do, I do as well for faster build times, but it also comes with like some issues, right? So if you run cargo clean, you just blow away like literally everything for every workspace, right? As well as like having like workspace specific files. We kind of don't want to pollute the cache with all of that over time, because then you'll just end up with another giant 240 gigabyte target directory. So here's like kind of the idea that we have for how we're going to design this. So I talked about like moving the build directory, the builder, into like cargo home, right? So like what we want to do is we want to move builder into cargo home, but we still keep it separated by workspace. So workspace path hash is kind of just a hash of the like workspace you're in. I'm not sure if there's a better way to do that, but that's like a current like placeholder variable that we support, and that's the current proposal. We're going to have like another directory like for the cache itself, which we'll talk about in a sec. And then you have your workspace, which has your target directory, right? So the artifact cache is at the cache, and then you'll have the artifact dir like stay where you are. So you'll still get your binaries in your workspace, which should be hopefully convenient. And the workflow for this is like you build into builder, and then you like when a build completes, you uplift that. We use this term uplifting cargo, which is basically just moving the file. We uplift that like build unit that we've compiled into the cache for later. And then we uplift your like artifacts that you care about into your target directory. And then finally, like the next time you rebuild, you can read straight from cache. And the idea behind that is that you can run cargo clean and like blow this thing away, but you keep your cache. And then if you have any like, project-specific files, it'll go in your build directory, not in the cache. And the cache will be like fairly conservative, and like we want to have like garbage collection, so that way it doesn't grow over time. I don't really love the term garbage collection because it makes people think like, oh my God, Rust is adding garbage collection. I like to call it cache pruning, but that's what it's called is like in the feature. Okay, so why is this better than the status quo, right? And so one, in theory, it will share like a lot of artifacts between workspaces, so we should have like less overall space being used up on disk. And you should have more cache hits overall, because if you've compiled the regex crate in one project and you compile it again, assuming your Rust flags and your feature flags all match up, which is a whole other thing, you should be able to reuse that. And then it also, one of the nice things is it centralizes all the build artifacts in a single place, so you should be able to like clean up things a bit easier. And one of the things I mentioned is cargo garbage collection. So Cargo has like the SQLite database that it uses to track accesses to like dependencies that you've used, and like crates that you've used, like that you've downloaded, and Cargo will over time clean those up automatically. It's a relatively new feature, like over the past couple of years, but it's not really extended out to all of the places Cargo stores things. So adding garbage collection to caching would be really nice. But what about locking, right? So we have this cache now that we're going to kind of contend on. So we can be kind of smart about the locking in the cache. So if a unit is in the cache, it means that we've fully compiled it already, right? We know that it has rlib and rmeta, so that simplifies our lives tremendously, because like pipeline builds are much simpler now, right? We don't need to like have this like, partially built state. We know everything's built. Yeah, so pipeline builds are less of a problem. Yeah, let me just quickly put everything out. So things that we care about, we don't want multiple cargos inserting into the cache at the same time, right? If you insert the same build unit, like what happens? Do they fight over it? We don't want to run cargo garbage collection while another cargo is compiling. Otherwise, like, a build unit would just be missing and your build would crash. And if we assume that these build units are immutable, which they're not, we're going to talk, well, I don't know if we're going to talk about that. That's a bit complicated. Then we don't really need to worry about if like we insert at the same time. And I'll talk about that. Excuse me, we won't need to worry if we're inserting while others are reading, and I'll talk about why. So we actually have like some prior art. So this is the cargo registry cache. So I've been talking about the build cache, but we actually have a different cache in Cargo called the registry cache. And this is whenever you download a crate file from crates.io, but you have not compiled yet. It's just the crate file. And we actually have a locking mechanism where it has like these multiple states. And this is one of the like prior arts that we used for the like previous locking design where we had two files. This is basically the same thing, except it's for the entire directory instead of a build unit. And the idea is that you can download while others are reading, right? But you cannot like clean it up while others are reading. And so it has this like download exclusive, this like shared. I'm not going to go into like the details of the registry cache, but I just wanted to share that like we have this prior art that we're kind of drawing from here. And so the idea is that we can allow multiple readers at the same time to the cache. And then we can allow a single appender even if there's other readers, because they're just going to be adding, like inserting into the cache, which is safe, right? But if you want to, but you can only have one appender at a time. Otherwise, like two might append to the same build unit. And then if you want to like clean it up, if like do garbage collection, then you need an exclusive lock. And this is kind of nice because it allows us to have more concurrency in this like directory, right? Like we don't have to limit to just one cargo running at a time. And also, whenever we like append to the cache, it's usually a very short operation. It's just a move of a directory, right? Like there's no compiling going on. Yeah, so it's much simpler, and it scales with large projects because it's like a constant number of file descriptors, right? There's just two files for the entire directory, or two locks. Yeah, and we expect appends to be very fast. So we can kind of take the append lock, pull in our file, and then unlock it immediately. So that's kind of like the high-level cache design that we have. I'm sure it's going to change because we're still in the idea phase. But I want to talk about remote caching, and this is even more hypothetical. So anything you hear me say, take it with a grain of salt. And so the vision is to build on the build cache that we just talked about, right? And so the idea is that Cargo has like a plugin ecosystem that allows Cargo to read from remote storage and then like kind of pull those build units in from remote storage into the build cache. Yeah, and the idea is that like these plugins can be developed independently of Cargo, and so either by organizations like say like a GitHubs of the world, or by individuals if they have their own specific thing they want to pull in. If you have your cache on like a Raspberry Pi or something for some reason, and then yeah, so the idea is that we let the plugins pull in like the cache into the build cache, and then from there it's kind of as if you had compiled it locally, right? Kind of having this idea of abstraction. That's the vision. That's all I have for that. There's like nothing else. Like it's all still kind of design. I wanted to give a quick like special thanks to Ed Page. He's been kind of like the biggest like mentor for this like thing I've been working on for the past year, as well as Wei Hong Lo. He's also another Cargo team member. He's also helped review pull requests and kept things moving along, as well as the rest of the Cargo team. These two guys were the most like involved, but everybody else in the Cargo team has been very helpful for this project. That's not my slide.
Is that the noun ONS readers?
I don't know what that is. Well, that's all, folks. That is the last slide. Alrighty.
All right. Wow. Okay. Cool. So that was amazing. I didn't know anything about Cargo. I don't know if you guys did, but I'm really impressed actually. That was super cool. But now we have pizza, and we also have non-alcoholic drinks for while we're in here. And then if you guys want to have some beer after, we have some stuff for that. We can go to another location.
Actually, why don't we ask Ross about his background?
Oh yeah. Well, I was getting there. So Ross, why don't you tell us about where you said you're from Texas? How'd you end up in Tokyo? And what do you do here? And what's your favorite hobby that you're doing right now besides working on Cargo?
Goodness. So yeah, I'm from Texas. I grew up on a very small farm out in Inaka. And
for English-speaking listeners, Inaka means the middle of nowhere.
And I was actually prepared for like Mate's like questions that he always asks. Like I prepared for those, and then you asked me like switched up ones. So I grew up on a farm out in Texas. If you don't know Texas, it's very hot in the summers, and so I would spend a lot of time like on the computer growing up, playing around with it. And then one day, like when I was in high school, my dad asked me, and I had never programmed anything before, "Hey, son, we have this pig farm, and we need a website because that's like what all of the important, like that's where all the money's at nowadays." It's like, I can make a website. Like I have no PowerPoint. I could do this, knowing like literally nothing about code. And so I went in and created this HTML website, no JavaScript. Looking back on that, I'm kind of proud of that. So yeah, it was HTML only with a little bit of CSS. I was Googling like, what is this CSS thing? And so yeah, we uploaded that, and that was my first forte into programming. Then I went into college, and my dad said, you should learn computer science because like you like computers. And I still didn't really know much about programming, but I was like, yeah, that sounds good. And at the time, I was really like not a motivated student at all. So it was kind of like, I'll do this thing. It sounds like an okay thing. And I didn't even know what programming really was my first year of college. And so I was walking around, and people would ask me, oh, Ross, what programming languages do you know? And I would say, HTML. I'm an HTML programmer. And like everyone else is like learning Java. And it was me. And I felt so cool saying that. And I look back on that, and I'm like, you were pretty cool. As for how I ended up in Tokyo, after the pandemic and the world shut down, I think I was watching, like, for whatever reason, like I had gotten on a Joe Rogan kick, and I was watching a lot of Joe Rogan. like podcast, and one of like he had a clip where he was like, to be excellent in life, like you need to do hard things, and I was really, I don't know why, I was really pumped up about that, and so I was like, yeah, I'm gonna do a hard thing, and so I'm gonna learn a new language while everyone's like at home playing video games during COVID. I'm gonna like learn Japanese, and why I picked Japanese, I don't know. And I'm gonna learn this in 3 months, and like, if you know Japanese, you know it's not really a 3-month project. And so, yeah, after a couple of years of study, I decided like, hey, you know what? I've been in Texas my whole life, growing up here. And so I was like, I'm gonna make a change and do something different, you know. So I decided like, okay, I'm gonna go to Tokyo. It's gonna be like the biggest change of my life, which it was. In 2020, in mid 2022, when the borders opened up for immigration, I got on a plane and flew over here, and I've been here since. So that's how I ended up here.
Okay, I have 3 more questions that I prepared. They're not the same as Mate's because I'm my own man.
Okay.
So even though we look the same. The first one is, what do you do now for professionally? I'm just going to give you all 3, and you can answer them at your own pace. The second one is, what was your muse before you discovered Rust, and why did you switch to it? For personal projects, at least. And the last one is, what's your favorite feature of Rust?
Okay, that's difficult. So professionally, I'm a software engineer. I spent 3.5 years at PayPay. I recently moved to a company called Cybereason. We're hiring, by the way, like 10 Rust engineers. So if you're interested in like cybersecurity, we're hiring. So I turned that into a pitch that will make my boss happy. Yes, I do software engineering at work. I actually use Rust at work as well, which makes me happy. What was the second one? It was...
what was your, after HTML, of course, what was your language of choice before Rust?
Okay, so I spent a long period of my career with like the traditional Java enterprise stack, Java, Spring Boot. My first company out of college, I was doing Java Swing, baby. Yeah, it was like a code base from 1998. Yeah, 1998. It was a Java Swing app with a Spring Boot backend. I think it was just Spring. It wasn't even Spring Boot. So yeah, I was doing a lot of Java. I kind of was really jaded with Java, so I had a JavaScript arc. So I was like doing like a lot of front end. Not as like my main thing. I was always like full stack. So I spent some time doing JavaScript. I wrote a Japanese language learning like tool called nihongostats.com. I'm kind of salty at WaniKani because they disabled their API a couple years ago, so it makes me sad. But yeah, and then in 2022, late 2022, I kind of picked up Rust and I immediately gave up. And then I came back to yeah, and then I came back to it in really early 2023, and I've really liked it because it solved so many of the pain points that I had with Java over the years, and like the nonsense reflection things, and you know, just blowing out the heap because Java decided that was what it wanted to do that day. Yeah, and the type system, I think Rust type system is really underrated. Like I hear a lot about memory safety, but like to me, the type system was what really draws me to Rust, and the efficiency, right? Like the memory safety is like, it's like, okay, that's nice, I guess. I'm coming from a garbage collected world, so that's not really a selling point for me. So yeah, and then I guess my favorite language feature of Rust, did it?
Oh, wasn't the type?
I guess it's the type system, yeah.
What about the types? You know, because they have, I mean, any good project starts with the data, but I mean, you know.
The enums are truly fantastic. Coming from Java, where, you know, very simple enums and TypeScript are like kind of frowned upon. So yeah, like the enums in Java and Rust are fantastic, and like the way that we handle null in Rust with option and result, I really love that approach. No more try catches, which makes me happy. I think that's a way better, more sane way to handle errors. So yeah, I guess that's probably my favorite feature, which is very basic, but like it's really core to the language, which I think is important.
All right, That's great. Well, next up, Lean and Haskell if you really like those kinds of types. So, well, thank you, Ross. That was amazing. I really just thought it was interesting, and thank you. I think your jokes are funny.
Okay, thanks. Somebody.
And yeah, so there's pizza. Monte picked a bunch of different flavors. Monte doesn't like tomatoes, so I'm sure there's even a white pizza. So dig in, enjoy. Thanks again, Ross, and thank you all for coming.
Yeah, thanks for coming.